So this is a very interesting concept, and let's see what that is. Definition. A graph is planar if it can be drawn on a plane without crossing edges. So, for example, this graph one, two, three, four. It has four vertices and 6 edges. This is a planar graph. It is not drawn in the good way because we don't want to have crossing edges like this. This is not a proper drawing, but the graph itself is planar because if you draw this in a different way like this, so it's 1, 2, 3, 4. Instead of drawing the edge between 2 and 4 directly, we can draw the edge in this way. You don't have to draw an edge like a straight segment. We can use like a curve or anything like that. As long as you don't see any two edges crossing each other, that's a good one. So here, there are no crossing edges. Let me draw the graph, all the edges without crossing edges, so it is planar graph. So it is an intrinsic property of a graph. It doesn't depend on how you draw the graph. It doesn't matter how you draw. As long as there is one way of drawing the graph without crossing edges, it's called planar. Okay? So to show that some graph is, a given graph is planar, you can just find a good drawing like this. If you show the graph like this, then you have just shown that the graph is planar because the graph, this is just proof. And let's see another example. By the way, this is a complete graph with 4 vertices. Complete graph means every 2 vertices are connected. Here is complete graph with 5 vertices. This is K5, right? 5 vertices, and every pair is connected. Every pair of vertices is connected by an edge. Is this planar? Right now we don't know because the drawing has some crossings. But maybe there is possible that if you draw this in a different way, maybe as we did over here, maybe it's possible to draw this without crossing edges. One may ask the question. This is the question that we will study today. And also this. Complete bipartite graph with 3 and 3 vertices each side. Like this. This is called complete bipartite graph, K33. Is this planar? Are these 2 graphs planar? So for instance, let's consider this. Let's try to draw K5 without crossing edges. So we have to connect everything from here, so let's do that. And from here, not very good. So connect this, and this, and this. And from here, or we can connect this, but we got stuck here. We cannot connect without crossing edges. So we cannot do this. But this is not a proof, because, you know, the fact that you couldn't find the proper drawing doesn't mean that it is not planar. Maybe if you arrange the 5 vertices in a different way, I don't know, like this, maybe it could be possible. But even if you show that it's impossible for this kind of arrangement of the vertices, there are another way of arranging the vertices. Infinitely many ways of drawing the curves. So you cannot really prove this by drawing. So if you want to show that, but if you try to draw this without crossing edges in several ways, and then you will be convinced that it seems impossible. But if you think that it is impossible, then you need to prove it, but not this way. You cannot consider all, because we cannot consider all possibilities. There are infinitely many. So how can we prove that K5 is not planar? We will develop some tools to show that K5 is not planar. All right, so a very useful theorem is this. It's called Euler's formula. So let's say G is a connected graph with V vertices, E edges, and F faces. Then V minus E plus F equals 2. So for example, the K4 that I draw without crossing edges, it's connected planar graph, I should say, planar graph. G is a connected and planar graph, and that means we can draw the graph without crossing edges. Just imagine that such a drawing is drawn there. And vertices and edges are just intrinsic properties of G, so we don't have to worry about this. But face, what is a face? What does a face mean for a planar graph? Face means you draw the planar graph on the plane without crossing edges, then the edges that will divide the plane into several regions. So each region is called a face. So here we have the outer face. Outer face is also a face, it's an unbounded face. And we have this one face, two face, 3, and 4, the outside region. So in this case, V equals 1, 2, 3, 4. E equals 1, 2, 3, 4, 5, 6. F equals 4, like we counted 1, 2, 3, and 4, including the outer region. And V minus E plus F is 4 minus 6 plus 4, which is 2. And this is always true for connected planar graph. Another example, it's true if this is not simple. G could be a non-simple graph. For instance, this. We have multiple edges and loop. So what is the number of vertices here? We have just 2, and edges 1, 2, 3, and 4. What is the number of regions or faces? 1, 2, 3, and 4, right? Again, 2 minus 4 plus 4 equals 2. This is true. And true for every connected planar graph. No matter how you draw because there are different ways of drawing this planar graph on the plane, but no matter how you draw, as long as there are no crossing edges, V minus E plus F equals 2. That's true. The proof is not that difficult, so let me prove it. Proof is done by induction. I'm going to prove this by induction on the number of edges, E, I mean. The base step would be E equals 0. There is no edge. That means because it's connected, we must have only one vertex, no edge, right? Then what happens to V? There's no edge because it's connected. We should have only one vertex, like this. And what is the number of regions? Just one, the whole region. F equals 1. Of course, V minus E plus F equals 1 plus 1 minus 0 plus 1 is 2. This is true. So the base case is done. Okay? So suppose that the theorem is true for the number of edges equals n. n is a non-negative integer. And now we will consider n plus 1 case. So consider a planar connected and planar graph, say G, with number of edges n plus 1. If you can show that G also satisfies v minus e plus f equals 2, then the theorem is also true for n plus 1 case, so it will be done for every e. So we will consider two cases. G has no cycles. G has no cycles. Then in this case, find longest simple path. So we don't have any repeated vertices in this path. So in other words, you just start with one vertex and then continue until you cannot go anywhere. You know, because the graph is finite, we have to stop at some point. We cannot go forever. So just take one longest simple path. Longest means you cannot go any further from here. Because there is no cycle, you cannot connect this with somewhere there. Okay? Then by the assumption, what is the degree of u? Degree must be 1. This is the only vertex connected to u. Because otherwise you can continue. Or you can connect, but because you don't have any cycles, the degree must be 1. And same for the degree of the other side. Degree 1 and degree 1. It's just okay that we find one vertex of degree 1. So here we have a vertex of degree 1. Let's say G prime is the graph G without, let's say G minus U. G minus U means you just delete the vertex U and the edge is connected to U. So we delete this edge and this edge. Okay, this vertex and this edge. We delete one edge and one vertex, right? Because the degree of u equals 1. Is that right? And in this case, what is the relation between v prime, e prime, and f prime in terms of v and e and f? So v prime means the number of vertices of g prime, and etc. What is the number of vertices in G prime? V minus 1, because we just deleted one vertex there. Okay, so only one vertex is removed, so V prime is V minus 1. What about E prime? We deleted just one edge, so it's still E minus 1. What about the faces? So G prime must be a planar graph, right? It is connected and planar, because we just deleted just one vertex connected to just one vertex. You know, if you have a drawing without crossing edges over G, then from there, by deleting one edge and one vertex, you still have a connected planar graph. So, and because if you remove this, you know, this part belongs to just one face, right? Because this is not a cycle. So you don't lose any faces. So it's just the same. Okay? And what is V minus E plus F then? This is the same because V is V prime plus 1 plus F, which is, what is F prime? V prime, E prime, F prime. But this is 2 because induction by induction hypothesis. G prime has one less edges than G. So by induction, we must have the Euler's formula. So it's true. That means the original graph, G with n plus 1 edges, also satisfies the Euler formula. Okay? So if there is no cycle, then it's okay. Now we have to consider the case when G has a cycle, at least one cycle. Is this fine? So case 2, G has a cycle. Then find a simple cycle. Simple cycle means you don't have any repeated vertices in the cycle. So maybe something like this. I don't know. There could be arbitrary cycles considered. And let's consider one edge, U and V, in the cycle. Okay? So G is this. So of course, this is not just a cycle. It has more complicated structure. We don't know. But it's like that. Okay? We don't know exactly. But we have at least one simple cycle like that. Okay, so let's say G prime be the graph G without the edge UV. I mean, just delete the edge, keeping the same vertices, same edges, except this edge UV. Just remove one edge like that. Okay? Then is G prime still planar and connected? Then G prime is connected, right? Because we deleted one edge, but it is in a cycle, so even though we delete this edge, everything is still connected, because if you have to use this edge, you can just forget about this and then you can just make a detour like this. So it's always possible to go from one vertex to another, even though this edge is deleted, because it is a cycle, inside a cycle. And still planar, because deleting an edge make it even more planar, you know. It's already planar, so it's deleting things cannot make it non-planar. And number of edges, what is the relation between V prime and V? We didn't delete any edge there, so V prime is equal to V. What is E prime? We deleted one edge, so it's E minus 1. What about F prime in terms of F? You can see here, because it's a cycle, this part belongs to one face, and this side belongs to a different face. They cannot be the same face because this is enclosed by a cycle. You cannot have a face having both this part and this part. So they belong to, this side belongs to one face, and this side belongs to another face. But if you remove this edge, then these two faces will merge into a one face. That means we lose one face, because these two combine into one thing. Okay? Is this okay? And what is V minus E plus F? So in terms of V prime, it is V prime. E is E prime minus 1. F is F prime minus 1. And again, we cancel these minus 1, so it's V prime, E prime, F prime. And by induction hypothesis again, because G prime has n vertices, n edges, induction hypothesis, this must be equal to 2. And we just show that the Euler's formula still holds for G. So Euler's formula is true. For G. And by induction, it's true for every graph, planar and connected. Any question? Okay, so this is a very nice and simple but very useful theorem. Let me tell you about this example. So K5, we want to show that K5 is not planar. So let's see if we can use Euler's formula. K5. So what is the number of vertices? 1, 2, 3, 4, 5. Number of edges of K5 is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 is 10. What is the number of faces? So here you can see the region is divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 regions, so F equals 12. So what is V minus E plus F? 5 minus 10 plus 12, which is 7. This is not equal to 2, so it's not planar. Okay. K5 is not planar. What do you think? Are you satisfied with this proof? A very simple proof, isn't it? Very simple and nice, only it's wrong. The only problem is wrong. This is not a correct proof. This is incorrect. Because V plus Euler's formula, let's go back to Euler's formula here. Here we assume that this is connected planar graph, then this is true. It doesn't say about the inverse. If this is non-planar, then this is not equal to 2. It doesn't say like that, right? And first, that's one thing. This correct statement is just one direction. It's connected planar. If you can use this only to connected and planar graph. And if it's connected and planar, we have this relation. And also, the critical mistake here is that we identify the faces in the wrong way, because when we talk about this planar graph and the regions or faces, we have to draw the graph in the correct way without crossing edges. Here, you see we have already crossing edges. This is not a good drawing, right? So for instance, suppose that you have this K3, if you draw this graph and something like this, then okay, I have 1, 2, 3, 4, 5, 6, 7 regions. It's not true. So you cannot do this. You have to draw the graph without crossing edges. If you draw the graph with crossing edges, you cannot count faces there because you don't really see faces there. So this is wrong proof. You cannot do this. Okay? Remember that. Because from this, if this is a good and valid proof, you can also prove that this is K3, K4 is also non-planar because V equals 4, E equals 6. What is F? If you count the faces like 1, 2, 3, 4, 5, this is 5. 4 minus 6 plus 5 equals what? 3. This is not equal to K4. You can conclude that this is also non-planar, but we already saw that this is planar. Okay? So you cannot really do this. So when you count the faces, you have to always draw the graph without crossing edges. Only in that case you can talk about faces. So far, we don't know how to prove that this is not planar just yet, but we need to develop more tools. All right. Okay, so let me define the notion of the degree of a face. So let's say G is a planar graph drawn on a plane. We also consider properly. because it's a planar graph, we can draw this on a plane properly. Here, properly means no without crossing edges. So, in other words, we consider the graph and the drawing together. And R is, say, a face of G in the drawing. So because we have a drawing without crossing edges, we can see the faces and just say, okay, this is our face R. Just consider one face. Then we can talk about the degree of R is the number of steps needed to walk along the boundary of R. So it's a little long sentence. So I'm going to explain this with an example. This actually is quite a simple concept if you see this example. Suppose that we have this graph, planar graph, drawn properly, right? We don't have any crossing edges. Here we have three faces. So let's say this is R1, this is R2, and this is R3. So we have three faces, R1, R2, R3. And what is the degree of R1? So that means, degree means you walk along that boundary. So boundary is this. So how many steps do we need? Or how many edges do we use? 1, 2, and 3, and 4. If you go this way, then by 4 steps you can complete the boundary of R. So the degree is 4. What about the degree of R2? Again, so you just go like 1, 2, and 3. So degree of R2 equals 3. What about degree of R3? The boundary of R3 is this thing. So you go 1, 2, 3, 4, and 5. If you go that way, then it's 5. So if your face is like an n-gon, then the degree will be n, right? But sometimes we have a little more complicated situation. So in this case, you can just consider degree as like an n-gon. The degree is the n. But sometimes we have things like, okay, maybe more complicated. Okay, let's say this. This is a perfectly good planar graph. How many regions do we have? We have 2, right? So it's R1, R2. What is the degree of R1? So here, when we compute the degree of R1, we just follow the boundary. So boundary is this. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the degree is 11. We just don't count the number of edges, but for instance, this edge is counted twice because we go along this at this side once and then the other side twice. So if the region planar, the region is not an n-gon, you cannot just consider that as the number of edges on the boundary. Sometimes some edge is counted twice. For instance, degree of R2, let's follow. You can start anywhere. So here 1, 2, 3, 4, 5, 6, 7, 8, 9. So degree of R2 is 9. So the degree of a region is defined like that. Any question? Okay, and there is a nice theorem about the degree of a planar region, planar graph. G planar graph. Let's consider connected. We will only consider connected. F set of faces of G. Then the sum of the degrees, so the region in our face F, degree R equals 2 times E, where E is the number of edges. Proof is actually quite simple. If you consider how we compute the degree of a face, it is kind of simple. For every edge, you can show that the degree, when you compute the degree, each edge contributes exactly 2 to the sum over here. Because there are 2 possibilities. Like, let's say we have E1, one edge, E1 here, where whenever you have an edge, you have 2 sides, or one side and the other side, and the 2 sides may be in different faces, or sometimes they may be in the same side, same face or region. Here, if they are in the different regions, or here, like this side and this side, right? Let's say this is R1, this is R2, this is R1. And E1, in this case, E1 contributes 1 to the degree of R1, right? And also contribute 1 to degree R2, because when you compute the degree of R1, you follow E1 just once. And over here, same. In total, the total contribution of E1 to the left-hand side is 2 in this case, right? And similarly, if you have an edge, like say E2, say, where these 2 sides belong to the same region, maybe connected some different way. So same region, say R3. This region is the same. In this case, E2 contributes 2 to our degree of R3. Only to this region, because for other regions we don't really visit this E2, right? So in any case, every edge contributes exactly 2 to the sum in the left-hand side. That means the sum is equal to 2 times number of edges. This is similar to the theorem, if you remember. This will remind you of this theorem. For all vertices V, degree of V equals 2 times number of edges, right? This is the first theorem that we learned in graph theory, right? And the proof is basically the same, because when we have an edge, E, or to E1, and if the edges or the vertices endpoint of E1 are V1 and V2, then E1 will contribute 1 to this vertex, 1 to this vertex, so to the degree of them. That's why we have this relation. And if we have a loop, then this edge, say U, this edge contributes 2 to the degree of U. Then this proof is kind of parallel to that thing. Okay? And now we can find some property of a planar graph using this theorem. Theorem G is simple connected planar graph with at least 3 vertices. Then the number of edges is less than or equal to 3 times the number of vertices minus 6. We must have this relation if G is simple connected planar graph with at least 3 vertices. Proof. Because G is a planar graph, we can draw the graph on a plane without crossing edges, right? So suppose that G is drawn on a plane properly without crossing edges, right? Like, I don't know, something like this. Just and by Euler's formula, right? Because G is planar, we draw this plane without crossing edges. You can apply Euler formula. By Euler's formula, we have V minus E plus F equals 2, where F is the number of faces. Okay? So far, simple. Now, by the assumption it's simple, connected, planar, at least 3 vertices, imagine a face of this graph drawn on a plane, right? In order to make a face, how many edges do we need? This is simple. Remember, this is a simple graph. We don't have multiple edges. If we have multiple edges, we only need 2 or even 1 edge to make one face, right? The smallest number of edges to make a face is just 1, if the graph is not simple, right? But we assume that graph is simple. So how many edges do we need to create one region? We need at least 3 edges. Triangle is the region having smallest number of edges possible, right? For a simple graph. Because it's simple, every face has at least 3 edges, or degree is at least 3, right? Because degree is the number of edges that degree is the thing that you follow the boundary. It can be even more than the number of edges if it is an edge sticking out like this. Okay? Do you agree? Every face has degree at least 3. You cannot have a face of degree 2 or 1. Okay? Because degree of 2 means we have multiple edge. Degree 1 means we have a loop. That's not allowed. Every face has degree 3 at least. And by the theorem, the previous theorem, we know that the summation R in our face, so F is the set of faces, degree of R equals 2 times E. Right? But what is the condition on this degree R? At least 3. Everything is at least 3. That means this is greater than or equal to what? If you add 3 every time, then this must be greater than that. So in other words, 3, right? This part, because every term, if you compare every term, this is greater than or equal to 3. But what is this number? 3. For every face, you add 3. That means it's just 3 times number of faces, 3f. Is that right? But now, what is f? We know from this formula, f equals 2 minus v plus e. So if you summarize this, 3 times f equals what? 2 minus v plus e, less than or equal to 2 times e. And now you can just simplify this. you will get this, which is the conclusion. And that's the proof. Okay? This is a nice theorem because it tells us some property that every connected simple planar graph satisfies. In other words, if some graph does not satisfy this, then it cannot be simple connected planar graph, right? So now we can really prove that K5 is not planar. Corollary, K5 is not planar. Proof. Suppose that it is planar. But we already know that K5 is simple connected, right? K5, you don't have any multiple edges, loops, so K5 is simple, and we know that it's connected. So K5 is simple connected planar. So by the theorem, previous theorem, E is less than or equal to 3, V minus 6. We must have this relation. Because K5, we assume that K5 is simple connected planar. But what is E? What is V for this graph? We have 5 vertices. What is the number of edges? 10. Just 5 choose 2 equals 10, right? And just plug this into the equation. So 10 must be less than or equal to 3 times 5 minus 6. This is 15 minus 9, 6, which is 9. This is a contradiction. This is a contradiction. That means our assumption must be false. So K5 is not planar. If you assume this, not planar. If you assume that this is planar, we get a contradiction. That means it cannot be planar. And this is a complete proof. We didn't have to draw all possibilities of the drawing. We can just say that planar graph must satisfy this, but this graph does not satisfy the property, so it's not planar, which is a very nice proof. Okay. In K33, the complete graph, complete bipartite graph, is also not planar. If you try to draw K33 without crossing edges, you always get stuck like 1, 2, 3, and then finally, if you try to connect this, and it's impossible to connect this dot with this without crossing edges. But of course, this is not a proof. It can be an evidence to your guess, but cannot be a proof. If you want to show that some graph is not planar, you need to prove something like that. Some property that every planar graph satisfies that. So let's see if we can prove that this K33 is not planar using the same theorem. So for K33, what is the number of vertices? It is still simple and connected. What is the number of vertices? 1, 2, 3, 1, 2, 3, so it's 6, right? What is the number of edges? 3 times 3, because we connect everything on one side to everything on the other side. 9, right? 3 times 3. So let's see if this is true. So here, this is 9, less than or equal to 3 times 6 minus 6. This is what? 18 minus 6, which is 12. This is true. Does that mean this is planar? No, doesn't mean that it's planar. So if the inequality holds, then we cannot conclude anything just yet. If the equality is not true, we can immediately conclude that the graph is not planar. But if the condition is true, the inequality is true, we cannot conclude yet. So there is some possibility that this could be planar. We cannot really say anything yet. So then how can you prove that this is not planar? We cannot use the theorem, the previous theorem. But for K33, we have some additional structure on this graph that we can use. That what is the condition? The crucial property of K33 is that it is a bipartite graph, right? It is a bipartite graph. What is a bipartite graph? Bipartite graph is a graph where we can divide the vertices into two parts, like A and B, so that every edge connects one vertex in A and one vertex in B. In other words, you cannot have an edge in A only or B only. Everything must be edge, something like that. So for a bipartite graph, we have a better inequality, more accurate or better inequality. So let me tell you the theorem. G is connected, simple, and bipartite graph. Oh, yeah, planar graph, of course. So many things there. Planar graph with at least 4 vertices. Then E is less than or equal to 2V minus 4. Proof. Again, we draw or consider one drawing of this graph. Consider that G is drawn because it's a planar graph. Imagine a proper drawing of G. And we know that by the same argument in the previous theorem, proof of the previous theorem, every face of G has degree at least 3, right? This is what we showed last time, in the last theorem. Because the 3 is the smallest number of edges to create a region, right? But now, this is a bipartite graph. Can we have a face of degree 3? If you have a face of degree 3, it must be a triangle, right? So a face of degree 3 is a triangle, like this. But can you have a triangle in a bipartite graph? In a bipartite graph, triangle is impossible. You cannot have a triangle. But bipartite graph, since because G is bipartite, there is no triangle. There is no triangle. No triangle. Why? If there is a triangle, you must be able to divide the vertices into 2 parts, so that you don't have any edge on one side only, right? So let's say XYZ. These are XYZ. And suppose that we try to divide the vertices into 2 parts. So we can assume that X is one side, right? X and Y are connected by an edge, so you cannot have Y on one side, on A, right? You cannot have Z there. That means you have to have Y and Z in the same side, right? But then you have an edge that connects 2 vertices in one side, so it's impossible. It's not a bipartite graph cannot have a triangle. In fact, bipartite graph cannot have a cycle of odd length by the same argument. That means, therefore, the degree of a face is always greater than or equal to 4, not 3. We have a better bound. Now the proof is the same. We use the same argument. So okay, let's see if we can finish this. So we know that 2 times E is equal to the sum of the degrees of the faces R in F, degree of R. But we know that this is always at least 4. So it's 4 times F, right? But what is F? You know, V minus E plus F equals 2. It's always true for any planar graph. So this is 4 times 2 minus V plus E. So if you simplify this inequality, this greater than or equal to this, then you will get the desired inequality. So that's the end of the proof. Okay. Now, using this theorem, we can prove that K33 is not planar. So corollary, K3, 3 is not planar. Proof. Like, suppose that is K33 is planar. But we know that it is bipartite, connected, simple. So it satisfies the conditions on the previous theorem. So by the theorem, previous theorem, E is less than or equal to 2V minus 4. We must have this inequality. But what is E? What is the number of edges? V equals 9. What is the number of vertices? E equals 3. So let's plug these into the inequality. We get 3 less than or equal to 2 times 3 minus, is it right? Oh no, it's just 6, right? It's 6. So 2 times 6 minus 4. So 12 minus 4, which is 8. So it's not, this is contradiction. That means this must be not non-planar graph. That's the end of the proof of this. It's very simple if you know the theorem. So we show that K5, K33, these are non-planar graph. Right? Can you imagine more non-planar graphs other than this? Of course, there are infinitely many non-planar graphs. So, so this is K5, right? Just add one more vertex and connect to this. Do you think this is a non-planar graph? Of course, this is non-planar graph. If you have a more if you add more edges or more vertices to a non-planar graph, the result is also a non-planar graph, right? Because already this portion of this graph is non-planar. You cannot have the full graph planar. So there are infinitely many planar graphs in this sense. But these, interestingly, these two are the essential non-planar graphs. These two are, in some sense, essential non-planar graphs. In other words, every non-planar graph must contain one of these. We have to define some terminology more precisely, but essentially, K5, K33 are, how can I say, are the essentially essential, okay, a little strange, but essential non-planar graph. other graphs just are graphs obtained from these by adding more things there. But we have to define this precisely. Okay. So let me give you a quick note. You know, suppose that this graph and this graph, these two graphs are different. They're not even isomorphic, right? They are not isomorphic graph because they have different number of vertices. They cannot be isomorphic. But as far as the planarity is concerned, these two are essentially the same graph. In this sense, if you can draw this without crossing edges, then you can also draw this without crossing edges, because adding a dot on an edge doesn't really change the fact that the graph is planar or not. If the original graph is planar, so suppose that you have some graph, complicated graph. If that's planar, if you add more edges, more dots on an edge like this, it is also planar, right? Because all you did was adding more dots. Doesn't change the planarity, being that it's planar or not. So here, this is the definition to deal with these situations like this. So let's say G is graph. So essentially, the definition that I'm going to tell you is about the property, or saying that they are of the same shape, not isomorphism, but not isomorphic, but same shape in some sense. So we say that a graph G prime is obtained from G by it's a little long sentence, series of reduction if we can construct G prime from G by doing the following things. The following. If G has a vertex of degree 2, what does that mean? G has a vertex of degree 2. It has edge going out one side and another edge going out one side. So it is somehow in an edge. So it means this vertex is an edge like this. So let me be more precise. So the situation is like this. We have a vertex V of degree 2. That means we have two edges like that. And change this into this. Just delete this edge, this vertex, and two edges, and then connect U and V by an edge. This is our operation. Okay? If you can obtain a graph G by doing this, you can do this many times, then we say that G prime is obtained from G by a series of reduction. For instance, this is obtained from this by a series of reduction, because we just delete this dot and connect this, keeping the edge. All right, now I need to define one more thing. Definition. G1 and G2, these are homeomorphic if G1 and G2 can be reduced to isomorphic graphs by a sequence of series reduction. By doing the thing that we delete, just delete the edge, vertex of degree 2, and then keep the two neighbors connected by an edge. So for example, let me consider this graph. These two graphs are homeomorphic. Homeomorphic. Why? From here, wait, maybe I'm doing this backward. You know, you can just remove these dots and then get this, right? And same here, you can remove these dots and then you get this. And you can see these are isomorphic. Then they are homeomorphic. So in other words, intuitively, you can see, you know, just ignore the dots and then just consider the edges. And if they have the same shape, then basically that means they are isomorphic. I mean, homeomorphic. Okay? But, you know, putting dots doesn't really affect whether the graph is planar or not. Because, you know, dot doesn't have any volume there. Okay? Now here is a theorem. This is a very famous theorem. It's called Kuratowski's theorem. And the theorem says G is planar if and only if it does not contain a subgraph that is homeomorphic to K3, okay, it doesn't matter, K33 or K5. So this is what I meant by the statement that these are essentially these are the essential non-planar graphs. Because every non-planar graph must contain this or this in a homeomorphic thing. Okay? So if G is non-planar, then this is, you know, is something. You can always find this kind of figure. You can always find this kind of figure or this kind of figure. It must contain something like this or something like this. Or some dots there, because that's homomorphic image, right? So these are the essential non-planar graphs. The proof is not so simple, so I'm not going to do the proof.